Okay. So this part of this webinar will be a talk about writing a key manager. So we will first talk about what is a key manager, why we need it. We will describe the key lifecycle functions in key manager. We will talk about selections, key validation, matching, and parameters of keys. We will cover relationship between key and an operation using the key, importing, exporting keys, and how keys are moved between providers. So what is a key manager? We have a key, which is an opaque object inside the provider. This opaque object is represented by a reference inside the EVPP key libcrypto object, which is again opaque, but there is a reference inside it. Even for the same algorithm, the representation of the key data inside different providers or even different provider versions can be very different. Currently, only asymmetric keys have a key manager. Asymmetric keys are handled just as binary data blobs that are passed into the respective interfaces as arguments or OSSL params. But in future, we probably will add a similar opaque key object for symmetric keys, and there will be key managers for symmetric keys and so on. So why do we need the key manager? Because we need to manage the key lifecycle. Sometimes the key will live only inside a single provider, which could be, for example, private key in hardware device. But in other cases, for example, public key decoded from a certificate, it might be necessary to transfer the key between providers. We need to even export and import keys into the application. We might need that. Here is a simple diagram. We have libcrypto, which loads FIPS provider and base provider, which is a typical use case, one of the typical use cases. The key manager in FIPS provider and in base provider is there to ensure the key can be moved between these two. Basically, the base provider can decode a key from some binary, for example, DAR encoded object or PEM file, and then it is exported out of base provider and imported into the FIPS provider, which does not contain any decoders because these are non-FIPS. These are not crypto algorithms. The decoding and encoding is not a FIPS algorithm, but it so it was like we did not include it into the FIPS provider because the boundary of the FIPS module would be too big or unnecessarily big. So what is a key manager in terms of a source code? It's a set of function calls into the provider. They do these following functionality. They provide this functionality: creating empty key or key by reference from a store, duplicating and releasing a key, generating a key, importing and exporting key data, validating a key, matching a keys, like two keys, getting and setting individual key parameters. The key manager is basically an OSSL algorithm, or it is represented by OSSL algorithm, which Richard was talking about in the previous talk. And it's identified there. Basically, the query function will return the OSSL algorithm with key management implementations when the OSSL op key MGMT operation ID is passed to it. This OSSL algorithm key is now terminated by this sentinel, and it can contain multiple key managers for various key types. For example, we have here only one key type, my key type 1, but there can be multiple ones like RSA, EC, any, basically what you can imagine. So there can be any number of those key types. The set of functions that comprise the MyKeyType1 key manager is contained in the MyKeyType1 key management funcs OSSL dispatch array. This dispatch array contains all the functions that the key manager consists of. You can see here only 2 functions, but there will be definitely more than that. This MKT1 new and MKT1 free function. The dispatch array, as Richard had in previous talk, it contains of ID, function ID, and the actual function pointer that's cast to this void function with void arguments, without arguments. Of course, the reference documentation is linked here in the provider key management man page, which you can read on the website or read as a man page when you install OpenSSL. Here we have a table of those key lifecycle functions that you will probably need in your provider if you want to support keys. You will definitely need a new and free function. The new function has a provider context as an argument that was also covered in the previous talk. And the free function receives this opaque key data object that you have created in the new function. These init, gen cleanup, and gen functions, they are useful for key generation. The first one returns a new key generation context object, which can be, again, something that your provider defines what it is, and it's completely opaque to libcrypto. Gen cleanup releases this key generation context, and MKT1 gen is a function that actually generates a new key, and it has callback to callback function as a parameter. I'm not mentioning that here all these functions in this table have their respective function identifiers. You can just imagine that those are in uppercase and has the OSSL func OSSL func key mgmt underscore prefix instead of MKT1 underscore. There could be also the duplication function, which is also key lifecycle function to duplicate the key data object, and there's also a function to create a new object from a reference from store, but that's kind of advanced topic, not for this talk. Here is an example of those new and free functions. We just allocate the empty key data structure and we return it, and we free it when the free function is called. Or we can of course do there any cleanup of any reference data that we have there. For example, if we had there some big nums, we would free them, but that's completely provider and algorithm dependent. The key generation follows the similar concepts as in AVP API. First, key or domain parameters based on the selection argument. A key generation context is created. It is possible to set parameters or template, which can be, for example, those domain parameters in case of key generation. And then the actual key generation is, or domain parameters generation is done, and the function returns a new key data object. Then the key generation context can be released. Now let's talk about selections, which is a new concept here that was introduced with providers. Selection is basically a bit field that indicates presence, applicability, or request of key components depending on a given function. It can be like in some function, it has like it could have rather like the meaning of there is this selection present, or in other function, it could be like apply this to this selection if possible, and so on. The individual bit flags are OSSL key management select domain parameters for the key domain parameters, such as the elliptic curve name for elliptic curves. The other parameters bit indicates any other auxiliary key parameters that the key can have. Public key, of course, is public key component, and private key is for private key component. There are also other macros defined that combine some of these bit flags. Again, please look at the manual page I've referenced before. And there are also combined bit flags that are part of the EVP API. There is EVP key private key, EVP key public key, and EVP key pair, which always contain not just the public or private key components, but also the domain and other parameters included. So the public key is always like public key plus domain and other parameters. Private key is, again, those three things. And EVP key pair is basically everything, but there is also OSSL key management select all that also includes all these components. As I said, the exact meaning of the selection is algorithm and function dependent. In some cases, having the selection bit set is mandatory, and the function must fail if the respective key component is not present. In other cases, it's just a request to apply the function to the respective key component if present, but the function should succeed if the component is not there. Again, I would refer you to individual manual pages of respective functions. There is one example here for key validation and matching. Here we have this selection parameter in all these functions. The has function should return 1 if all components in the selection is present. This function, if there is a public key component and the selection contains public key bit, it should return 1. But again, there is something that's algorithm specific, because, for example, the RSA keys don't really have domain parameters, for example, or other parameters. So this function basically ignores the domain parameter selection bit. It behaves as, at least in our provider implementations, it behaves as the domain parameters were always there for RSA keys, because otherwise, like, it would have like bad usability problems. The match function The match function is a test for equality of key data based on the selection again. The comparison, if the comparison of both public and private key components is requested in match function, but one of the two compared keys does not have, for example, the private key component present, the two keys can still match if the public key component is equal. Of course, it's not possible to match keys if the present components cannot be compared. If one key has only private key component and the other key has only public key component, then it would not be possible to match them. Even if it was possible to compute the public key from, for example, from the private key, which is possible with some algorithms, it is not expected like that this function will do anything computationally intensive. It could have even security implications if you do this in a provider. So this function should really just try to compare those and not compute anything special or any special computation for doing this comparison. The validate function checks if key data contains valid data subsets indicated by selection. It can also check consistency of the public and private key component if the selection contains both public and private key bits. It can do this key pair check. And the check type argument is to indicate whether the check should be like quick or full, which could be really computationally intensive, the full check. Now the keys probably have some parameters usually, and to get them and set them, we have these 4 functions. It's very similar to other functions in providers that do something with parameters, that we usually have some get params and gettable params call, and set params and settable params calls. So the get params call gets parameters of keys. It could be any auxiliary properties of keys, but also key components. And the gettable params will give you or should give the list or array of gettable key parameters. Similarly for set params, sets parameters of keys, but usually not key components, because it's beneficial to have keys immutable to set params. So set params and settable params functions don't have to be implemented. But for pre-existing key types, it would require significant application changes in comparison to what was possible with 1.1.1 versions. So unfortunately, for example, setting the public key component of a key that contained previously only domain parameters, it is possible with our providers, like with the Diffie-Hellman key type or EC key type. In some cases, the algorithm name for a key operation is different from the name of the key type. Yeah, because the EC keys, for example, can be used for ECDH and ECDSA at once, or for both of these operations. For this reason, we have this query operation name function in the key manager dispatch array, which should return the operation name for this operation ID for this key type that we implement. So here we have, for example, returning my key type 1 sig for the signature, and my key type 1 kex for the key exchange algorithm. But if the key type name is the same as the operation name or names, this function doesn't have to be implemented. For example, RSA supports multiple operations, all with the RSA name. DSA supports just DSA signatures, so there is also no point to have this function implemented. More modern algorithms, such as the post-quantum ones, don't support actually multiple classes of operations for a key. So, and this is not a disadvantage, yeah, because reusing the same key for different operations can have bad security consequences, and having a separate key type actually actively prevents to using a key for the same key for example, signature and key exchange. Now we are getting to the importing and exporting the key data, which is used to basically move the data between various providers and application. The import function imports the data from the OSSL param array according to the selection and into an empty key. Yeah. My personal opinion is this should have been a constructor function, but it is not. You need to first you need to call a new function, and then you will use this newly constructed key data to import. Again, MKT1 import types X function returns of params that comprise this key selection for import. Basically, it will tell you which parameters should be returned or should be passed into the import function to create the key or import the key. MKT1 export function is a function to export a selection as params through the param callback. So basically, this function should create an array of params, OSSL params, that's passed then into this param CB function. MKT1 export types X again returns array of params which you can use to see which params are comprise a key for export. Both import and import types X functions must be implemented at the same time. It is, of course, possible to not support key import at all. Typically, hardware device that does not allow importing keys does not necessarily have to have import function implemented. There is also the import types function that does not have the prof_ctx argument, and that function can be implemented instead if you need compatibility with OpenSSL 3.1 and 3.0 releases, or if the provider CTX argument is not needed in this function, which is actually the usual case. For example, the default and PIPS providers don't implement the import types X function, but import types function only. And the libcrypto ensures that basically both one of these it checks which of these functions is implemented and calls the one that is implemented. Of course, the import type X is preferred if it's available, but if it's not, import is called. Typically, the import function is like created, is called from EVPP key from data, and the import types X is called from EVP key from data settable. Similarly, for export and export types X functions, basically everything I said on this previous slide applies to those. They must be implemented at the same time, and exists the backwards compatibility export types function. Export is typically called from EVPP key export and EVPP key to data functions. Export types X actually has currently no caller from EVP API. So you could say that you don't have to actually implement it, but if you want your provider to be compatible with future versions of OpenSSL, probably should rather implement it. And if the requested selection that's important to know, that if you implement the export function, if the requested selection is not exportable, the export must fail. Yeah. So if you don't export public key if the private key is available and cannot be exported. If you have HSM provider which cannot export private keys and should not export private keys, then if the export function selection argument is set to OSSL key management select private key, you should fail the export function or return failure. How keys are moved between providers. The operation implementation is selected based on a property query. For example, a given provider might not support the operation at all, or that's typically providers don't need to implement encoders and decoders if they don't want to support any special encoding and decoding or data in some special format than the OpenSSL currently supports. If the operation implementation is in a different provider than the provider that holds the key originally, the key data needs to be somehow copied between providers. But the key data inside the provider is completely opaque between providers. So what is done here is that the key export is automatically called from the source provider with the export callback being a function that imports the key into the destination provider. And what happens when key data cannot be exported from the source provider? Typically, this is the HSM, some hardware device or smart card that does not allow unencrypted private key data export. The key export of the private data will fail. And in such case, libcrypto does this special fallback, which even if the property query prefers another provider for the operation, the source provider will be used instead. Of course, the property query must allow to use that provider. So, for example, typically you would use provider not equals myprof, which will still allow to use myprof for private key operations, but it won't be used for any other operations. And that's it.